This tutorial is aimed at describing the functioning of the iRRLS application for iCub, aimed at solving the regression problem for the inverse dynamics of the iCub limbs. In particular, we'll focus on the right arm in this tutorial. Our inputs will be the position, velocity and acceleration for the first four arm joints of iCub, so related to the shoulder, the tree in the shoulder plus the joint in the elbow. And the output are the it's a 6-dimensional range measured by the force torque sensor placed in the arm of the iCub. This is the overview of the application, which is based on the GURLS library, Grand Unified Regularized Least Squares library, and it works in real time on the iCub robot. It's been tested on the black robot. The motion of the arm has been recorded while the end effector moved inside the bounding box of predefined size, and the estimator works as follows. There is a batch pre-training and model selection based on the RLS regularized least squares algorithm. Then the input is mapped according to the random features framework, and after the pre-training the algorithm works online and performs an out-of-sample prediction and error estimation for the real and for the stream of samples coming from the sensors, and then it performs a recursive update of the estimator in order to adapt the model to changes in time. This is the outline of the application, where we have the state of the arm, in this case the right arm, as input, and the output of the sensor, of the force torque sensors, as the labels of our problem, of our machine learning problem. They input into a synchronizer module in which the velocity and the acceleration at the joints are estimated using the velocity observer module. The velocity observer libraries available on Robotology in the iCub-main repository. Then the synchronized vector containing position, velocities and acceleration plus the forces and the torques is sent to a normalizer, which normalizes the data, and to a random feature mapper, which performs the mapping to the random feature space. Then the mapped data is sent to the RLS estimator module, which performs pre-training either from a file or from the input stream directly from the online operation of the robot. It can be pre-trained on a number of samples which can be specified in the configuration file of the estimator, and then it outputs the predictions and the performances. So now let me show you an example of the operation of the application. So this is the set of instructions to perform. So we open a fresh terminal, launch YARP server, of course. Then we run the dataset player, since we have dumped the data taken from the black robot. So we launch the dataset player application, and then we open the directory in which we have saved the ARM data. So in this case it's the right arm. Just wait a minute for it to open the dataset. Now the dataset has been opened, and we can start the streaming directly. So now it works as if the robot was connected to our system, and now we can start running our application. Running first GYARP manager and looking for the application called iRRLS. You can see the modules composing the application on the right. We will launch the synchronizer, random feature mappers and normalizer, and also 3 YARP scopes for visualization reason, and the iCub-GUI in order to see how the robot is moving. The iRRLS estimator will be launched from the terminal in order to see the output of the module, which is pretty interesting. So we first run these, and then we connect, and then we run the iRRLS estimator module in this way. iRRLS estimator with no parameters, since everything has been configured in a .ini file. We run it, and it's waiting for the first samples in order to perform pre-training. Now, in order to start everything, we need to launch all to connect all the modules, just simply connecting everything. And on the left, on the iCub-GUI, you can see, of course, the motion of the arm according to the dumped dataset. We are using the right arm. It's moving randomly inside a bounding box. So now let's move to the terminal. At the moment, the iRRLS estimator is receiving the mapped data, and it's waiting for 5,000 samples, which correspond approximately to 4 minutes of operation, 4 or 5 minutes of operation of the robot. It's waiting for 5,000 samples for pre-training and model selection. So now we have to wait until the counter arrives at 5,000. In the meantime, I will show you the YARP scopes. Okay, these are the signals coming from the force torque sensors. These are the force signals along the 3 axes of the sensor, and we'll have to estimate this signal from the position, velocity and orientation data. We'll soon see the prediction in these graphs as soon as pre-training terminates. We have the same graph for the torques here. Torques measured by the force torque sensor. The functioning is exactly the same. So now we have arrived at approximately 3000 samples. The robot is still moving, of course. The dumped dataset we are using has been recorded for about 1 hour and 10 minutes, so we have plenty of samples to use. Okay, now we are almost there. We are almost arrived at 5000 samples, and the iRRLS estimator will perform a batch pre-training and model selection, and then it will start streaming the predictions. Now it's streaming the prediction. It's very fast to pre-train. And now we'll look at the predictions. Here for the forces, as you can see, the predictions are shown in green, and they overlap with the real signal pretty well. And for each prediction, there is after the prediction we have an update. So here the model is continuously updating itself based on the incoming data. So these are the forces. For the taus we have the same behavior. Here we have a visualization problem, but it's the same thing. And this is the graph containing the performance measure, in this case the root mean square error for the predictions. This is very interesting to see that in the beginning we have an error of approximately, for the forces is approximately 0.5 newtons, and it settles around 0.2 newtons, while for the torques we have a similar behavior from 0.04 settling around 0.02 newton meters. Okay. The robot is still moving randomly, and we have set up the module such that after 3000 prediction and updates, it will save a matrix containing all the predictions. Sorry, containing all the performance measures for each output, in order for us to be able to post-process them and make a graph similar to the one we have seen in the YARP scope. So now, after 3000 samples, the specified number of predictions have been reached, but we can of course modify the configuration file of the estimator in order for it to perform a continuous operation without stopping. And the error measurement matrix has been saved. We'll now look at it. It is saved in the directory from which the experiment has from which our RLS estimator has been launched. So this is the stored error matrix in the home directory. And there is a way to define the number of experiments we want to carry out. For example, if you want to repeat the process 6 times, we can specify it in the configuration file. This thing has already been done, and I will show now the graphs plotted with MATLAB, starting from the dumped matrices. These are the graphs we have seen for the forces, for the torques, and for the errors. and these are the repeated tests results. You can see that the root mean square error stabilizes around 0.25 newtons for forces, for the average forces along the 3 force axis of the sensor, and the standard deviation is quite small, while these are the results for the torque estimation, settling around between 0.025 and 0.03, again with a quite small standard deviation. The model selection is completely integrated within the GURLS library, so it is performed online. It is performed in the pre-training phase automatically. These are the references to the GURLS repository and to the iRRLS repository containing the code which has been used in this tutorial.